Ladies and gentlemen, welcome to. Wait, was that the wrong contract? Okay, I was, doing the voice for WWE there. No, that was a joke, by the way. No, so today we're gonna talk about rational functions. Okay. Now, before we talk about rational functions, I want to ask you a question. I don't know how many of you will know this question, but I'm gonna ask it first. Do any of you know what the meaning is of a rational number? Many students don't. They just know that, let's say, 1/2 is rational, but maybe pi isn't. So, from now on till forever, or in other words, to use the fancy Latin phrase, if I want to sound super snarky and super uh, like stuck up, I could say mutatis mutandis. Nah, I'm just kidding. But from now on, I want you to know that a rational number is any number that can be expressed as a fraction of two integers where the denominator integer is not zero. Okay? Now, it's not technically important that you know this definition at this stage. Um, However, I did want to let you know that as a prequel, that will make this make more sense. Okay? So, what we just said was that rational numbers are numbers that can be expressed that can be expressed as quotients of integers where the denominator is not zero. And so that motivates us to realize that this definition is kind of like an extension of that idea, okay? Or it gives us an idea of why these are called rational functions. I mean, I'm sure none of you thought that these were rational functions because they're the opposite of irrational functions, whatever those might be. Okay, that was a joke, of course. Yes, that joke appeared to look like it was landing, and it just never hit. Okay, in all seriousness, we say that a function f of x is rational if it can be written as a quotient of two polynomials. Okay, that is, if it can be written in this form. If you notice, I have a polynomial up here on top, and I have a polynomial on the bottom. Okay, and and also I want you to be very clear. On the top I put power n, on the bottom I put power m. Now that's not to say that n is always on top or m is always on the bottom. That's to say that I did not assume the power was the same. And I'm also not assuming that they're different. I just wrote it like this to emphasize the extreme to emphasize that this is in full generality. I do want to also point out that in this particular representation, I have written it so that the powers of the polynomial on the top and the powers of the polynomial on the bottom are from greatest to least. Okay? Okay. So now I want to make one brief, and I hate to say this, highly technical note before we move forward, but I'm going to make it anyway because I think it's important. In this definition, I have defined this as a rational function, but everything that we're going to discuss in this section holds true if we were just looking at it as an equation instead with some rational expression. Okay, so y equals to some rational expression. Okay, so yeah, and so so in other words, our discussion that's going to follow will carry over if we wrote it in this manner. Okay, and I want to remind you at this point what the difference is between the perspective of the function perspective and the equation perspective. Okay, I don't want to lose sight of that real quick. Remember that the function perspective, we look at an expression like this and we say, aha, there's a function named f. By the way, I don't think that you should ever think of it this explicitly, but I want to know that you can interpret it this explicitly, and it'll help you to think about certain cases. So the function interpretation would be like this. There is a function named f which takes an input x and which outputs this expression with that value of x substituted. So if I wanted to calculate the f of, let's say, the number, let's say represented by c, then I would rewrite this as a to the n times c to the n plus a to the n minus 1 times c to the n minus 1 plus dot 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 plus a1c plus a naught divided by bm times c to the m plus bm minus 1 times c to the m minus 1 plus b1c plus b naught, and then I would simplify it until I got a final answer, okay? Or a numeric answer if the c was actually a numeric value. If I was actually talking about evaluating the function at the variable c, then what I said out loud would have been the case, except for the dot dot dot. We don't know what's going on here, right? But we will in the examples that follow. That's the function perspective. The function is, we have some function named something, it takes some input and it outputs some value. The equation perspective, just to remind you, just to recall this important thing, the equation perspective is that this is a statement that is conditionally true, okay? And that any point xy that makes this equation true will be part of the solution set of this equation, and so it'll be part of the graph, right? Because the graph of a function consists of the points that make the equation true, okay? And it's just a little change in perspective that I don't want you guys to forget about, okay? But with that said, right, we're going to proceed forward and look more carefully at rational functions, okay? Okay, I hope you've enjoyed this, and let's get started.